morning guys, my name is Alhakim K. Sahial Jr. For today's video, we talk about red-black trees. What is a red-black tree? A red-black tree is a self-balancing binary search tree. That is, a binary search tree that automatically maintains some balance. Each node is assigned a color, red or black. A set of rules specify how this color must be arranged. E.g., a red node may not have a red children. This arrangement ensures that the tree maintains a certain balance. After inserting and deleting nodes with complex algorithms are applied to check compliance with the rules, and in case of deviation, to restore the prescribed properties by recoloring nodes and rotation. NIL nodes in red-black trees. In the literature, red-black trees are depicted with and without so-called NIL nodes. An NIL node is a leaf that does not contain a value. NIL nodes becomes relevant for the algorithm later on, e.g., to determine colors of uncle or sibling nodes. In Java, NIL nodes can be represented simply by nu11 reference. More on this later. Red-black tree example. The following examples show two possible representation of a red-black tree. The first image shows the tree with IE with implicit INL leaves. The second image shows the tree without explicit INL leaves. This is the sample of red-black tree within implicit nil leaves. That's the sample. This is the another example of red-black tree without implicit NIL leaves. Red-black tree properties. The following rules enforce the red-black tree balance. Each node is either red or black. The root is black. All NIL leaves are black. A red node must not have red children. All paths from node to the leaves below certain the same number of black nodes. Rule 2 is in parentheses because it does not affect the tree's balance. If a child of a red root is also red, the root must be color black according to Rule 4. However, if a red root has only black children, there is no advantage in coloring root black. Therefore, Rule 2 is often omitted in the literature when explaining the insert and delete operation, and in the Java code, I will point out where there would be difference if we would also implement Rule 2 so much in advance. The difference is only one line of code per operation. By the way, from Rule 4 and 5 follows that a red node always has either two NIL leaves or two black child nodes with values. If I had one NIL leaf and one black child with value, then the paths through this child would have at least one more black node than the path to the NIL leaf, which would violate Rule 5. Height of a red-black tree. We refer to the height of the red-black tree as the maximum number of nodes from the root to a NIL leaf, not including the root. The height of the red-black tree in the example above is 4. Rule 3 and 4 follows. The longest path from the root to a leaf, not counting the root, is at the most twice as long as the shortest path from the root to a leaf. That is easily explained. Let's assume that the shortest path has, in addition to the root, and black nodes and no red nodes. Then we could add another and red nodes before each black node without breaking Rule 3, which could reward no two red nodes may follow each other. The following examples show the shortest possible path through a red-black tree of height 4 on the left and the longest possible path on the right. This is the shortest and longest path in a red-black tree. Red-black tree Java implementation. As a starting point for implementing the red-black tree in Java, I use the Java source code for the binary search tree from the second part of the binary tree series. Nodes are represented by the node class. For simplicity, we use int primitives as the node value. To implement the red-black tree beside the child node left and right, we need reference to the parent node and the nodes color, we store the color in a boolean defining red as false and black as true. Implement the red-black tree in the red-black tree class. This class extends the base binary tree class presented in the second part of the series, which essentially provides a get-root function. We will add the operation insert, search, delete in the following section step by step. But first, we have to define some helper functions. Red-black tree rotation, insertion, and deletion work basically as described in the article about binary search trees. After insertion and deletion, the red-black rules see above are reviewed. If they have been violated, they must be restored. That happens by recoloring nodes and by rotation. The rotation works precisely like with AVL trees, which I described in the previous tutorial. I show you the corresponding diagram again here. You can find detailed explanation in the section AVL tree rotation of the article just mentioned. Right rotation. The following graphics show a right rotation. The colors have no relation to those of the red-black tree. They are only used to track the node movements better. The left node L becomes the new root. The root N becomes its right child. The right child LR of the pre-rotation left node L becomes the left child of the post-rotation right node M. The two white nodes LL and R do not change their relative position. This is the right rotation in a red-black tree. The Java code is slightly longer than in the AVL tree for the following two reasons. We also need to update the parent reference of the nodes. In the AVL tree, we work with a parent reference. We need to update the reference to N from the pre-rotation top nodes. Parent N in the graphic. For the AVL tree, we did that indirectly by returning the new root of the rotated subtree and the hooking the rotation into the recursive call of the insert and delete operation. Left rotation. Left rotation work analogously. The right node R moves up to the top. The root N becomes the left child of R. The left child RL of the formerly right node R becomes the right child of the post-rotation left node. N, L, and RR do not change their relative position. This is the left rotation in a red-black tree. Red-black tree operation. Like any binary tree, the red-black tree provides operation to find, insert, and delete nodes. We will go through this operation step by step in the following section. At this point, I would like to recommend the red-black tree simulator by David Gals. It allows you to animate any insert, delete, and search operation graphical. Red-black tree insertion. To insert a new node, we first proceed as described in the binary search tree insertion section of the corresponding article, i.e., we search for the insertion position from the root downwards and attach the new node to a leaf of half leaf.